Hi, this is Craig Stocks here at Utah Desert Remote Observatories. You can find us online at utahdesertremote.com. And the video today is going to be a little bit different. This is an excerpt from a talk I gave to a group of high school students who were taking an astronomy class, and they wanted some information about what is astrophotography. So this is a portion of what I shared with them. So to start with, let's look at where we live. We live in the Milky Way, obviously. You probably already know that. And when you look up the night sky and you see that streak, that's the Milky Way, although in reality, pretty much every star you see is part of the Milky Way. We live in this section or a section of the Milky Way. The bright part that you see in the sky is the core of the Milky Way, and we really can't see through that, so we don't really know what's on the other side, but we assume it looks pretty much like what's on this side. And most of the things that you might be familiar with in the night sky, such as the Orion Nebula, the Eagle Nebula, which is where the pillars of creation are found, the Lagoon Nebula, most of these things, these real popular targets, are right in our little section of the Milky Way. Now, the Milky Way itself is about 100,000 light years across. It kind of fades out, so it's hard to say exactly how big it is. Somewhere between 100 billion and 400 billion individual stars. I don't think anybody has actually counted them, but there's lots of stars. It's about 100,000 light years across, and most of the stuff that we see that's in the Milky Way is within 5 to maybe 30,000 light years, so pretty close within the Milky Way to where we are. And we're about, I don't know, 2/3 of the way out from the center. When you look up the night sky and you see that streak, the brightest part that you see in the summer is the galactic center. So when you see that bright part, you're looking into the core of the Milky Way, and that's also where the supermassive black hole that we call Sagittarius A star. That's the Milky Way's supermassive black hole that's at the center. When I use the term astrophotography, I'm usually referring to photography through a telescope, photographing objects usually outside of our solar system. There are specialties of planetary photography where people photograph Jupiter, Saturn, Mars, the other planets within our solar system. And of course, lunar, taking pictures of the moon, or solar, taking pictures of the sun. And those are really astrophotography specialties. Generically, usually astrophotography refers to taking pictures through a telescope. There's a lot of uses for astrophotography. My main use for it, and what a lot of people do, is just to make pretty pictures. But there's a lot of scientific value, tracking the variation in star brightnesses, finding and confirming exoplanets, determining the composition of stars and galaxies, determining the motion, speed, and distance of stars and galaxies. And really, all astronomical science is done with a camera through a telescope rather than through an eyepiece. The days of doing astronomical science looking through a telescope, I think, are well behind us. It's all done with cameras. There are different kinds of things that you might point your telescope at in two very broad categories. Are nebulae, which are blobs of dust or gas, and generally within our galaxy, in that 5 to 30,000 light years away. And other galaxies. Of course, the Milky Way is not the only galaxy. There are billions of galaxies. Some are close enough that you can get pretty decent images of them with amateur telescopes. An example is Bode's galaxy, which is 12 million light years away. So remember, our Milky Way galaxy is 100,000 light years. This galaxy, Bode's galaxy, is 12 million light years away, so a long ways away, well outside of our galaxy. The nebulae that you look at are generally within our galaxy. There's different kinds of nebulae. Reflection nebulae are common, and it's basically dust that's being illuminated by one or more bright stars. Uh, there's nothing really special going on. It's just dust floating around in the Milky Way galaxy, and there's a star lighting it up bright enough that we can see it. There are also emission nebulae, and these are a different category. These are generally made of gases like hydrogen, oxygen, sulfur, very, very faint and diffuse, but that gas is being energized by electromagnetic radiation, the gamma rays coming off of stars, sometimes by mechanical activity, a shock wave from a supernova moving through the gas. But something is putting energy into this gas, and enough energy that's causing it to glow. So it's glowing much like a neon lamp would glow when you energize the gas within the lamp. And every element has its own color that it glows. So you get different colors being emitted by these different types of gases. It's very faint. Generally, you can't see it by eye, but with a camera, you can photograph it. A special category of emission nebulae is a supernova remnant. So this is stuff that was blown out when a giant star blew up. So this is stuff that started out in a star and got blasted out into a supernova. And sometimes it's also being energized by that shock wave. There are dark nebulae that look like spots where there aren't stars, and what it actually is clouds of dust that are dense enough to block the starlight from beyond or behind it. So it looks like a hole in the sky with no stars. It's actually just a cloud of dust blocking the stars. And then there's a relatively recently discovered form called integrated flux nebula. And this is very large, very faint clouds of very fine dust that's usually not close by within the Milky Way, but kind of on the outskirts. And it's being illuminated by the combined starlight of all the stars in our galaxy. So the term integrated flux nebula, integrated flux just means combined light. So the combined light of the stars in the galaxy are illuminating it enough that we can photograph it. And we don't have a monopoly on nebulae. If you look at some of the nearby galaxies, such as M33, which is the Triangulum galaxy, or the Andromeda galaxy, those galaxies have nebulae within them also. And you can photograph the nebulae within distant galaxies. So that's a little bit of a special form. You need a pretty big telescope if you want to actually get a close-up of those nebulae, though. So how big are these things that we're looking at in terms of angular size? How big do they appear? Well, if we look at the night sky, and what we're looking at here is the Orion Nebula. There's Orion's belt, and the Orion Nebula is actually right here. So if we draw a box and zoom in on that and take a long time exposure, what we find is there's actually a whole bunch of stuff going on there. You've got huge clouds of ionized, mostly hydrogen, that is glowing and giving off light, as well as dust clouds like this Witch Head Nebula over here. So it's a mixture of both dust and ionized hydrogen that's glowing. Again, if we draw a box and zoom in, this is the rather well-known Horsehead Nebula region, and this is the two stars of Orion's belt. And if we zoom in again, now we're looking at a closer view of the Horsehead Nebula, the Flame Nebula, and again, dust that's blocking stars and ionized gas that is glowing and giving off light. So we've zoomed in several times, but if we superimpose a moon at its size relative to what we're looking at, you can see that the area that we're looking at is still pretty large. I mean, it's 3 times the size of the full moon, both across and vertically. So it's really a large area. You don't need a real long, high-powered telescope to photograph a lot of this stuff. What you need is time for the exposure. So a couple of terms that you may hear people use, tracking, that as you know, the Earth is turning, and that causes the stars to appear to move overhead. The same thing that causes the sun to rise and set. The stars also rise and set, just like everything in the sky. The goal is to have nice pinpoint round stars, but since the stars are moving, the telescope has to move with the sky and track those stars across the sky. And that allows for longer exposures and also longer focal length so that you're photographing stars as pinpoints and not as star trails. We also use stacking, which is taking multiple frames and then averaging them together. And the reason is when you average the images together, the digital noise that is always present is random and it gets averaged out. So you get a cleaner image with more detail by taking many exposures and combining them together. So images are really assembled from multiple exposures rather than being just a single long exposure. Exposures would typically range from maybe 60 seconds up to 20 minutes or even longer, but that allows the random noise to be averaged out. And we also combine images that are taken through different filters. And when I say filters, I'm talking about actual pieces of colored glass that you put in front of the camera when you take the picture. Here's an example of a single frame. I don't know how well this comes through in the video. And here's an example of 8 frames averaged together. It's cleaner, there's more detail, and you may notice also this satellite trail that was going through the single frame. When you combine frames together, that gets averaged out. There's really 2 kinds of cameras or 2 approaches that are used in astrophotography. You can use a color camera, which takes a color photo just like your telephone or a DSLR. In fact, you can use a DSLR. You can also use a monochrome camera, which is, it only takes black and white photos. It doesn't take any color. Color cameras are popular. The images are easier to process. And they're really the best choice for some targets, such as planets and comets, where things are moving fairly quickly. It's much easier to work with a color image from a color camera than from a monochrome camera. Monochrome cameras, you must use a glass filter of some sort, otherwise you're just getting just a simple black and white image. Post-processing does become a little bit more complex, but it does reveal, and sometimes a lot more detail. And when you think about any of the large telescopes like the Hubble or the James Webb or any of the big telescopes you can think of, all they use is monochrome cameras. There are no color cameras on the Hubble or the James Webb or the big science telescopes that are in Chile or Hawaii. Those are all monochrome cameras using various filters. Most common filters are LRGB-SHO. That stands for luminance, which is just a clear filter. Red, that photographs just red light. Green captures just green light. Blue captures just blue light. And those are considered broadband filters. And then there's narrowband filters for sulfur, hydrogen, and oxygen. And we'll talk a little bit more about how you use those. Our images, color images that we're used to looking at are usually produced through a red, green, blue combination. If you're watching this on a phone or a monitor, that monitor is using a combination of red, green, and blue. And when you combine it in equal amounts, it creates a neutral or a white light. So when you photograph through, if you want a color image with a monochrome camera, you would photograph using a red filter, and then a green filter, and then a blue filter. So you have 3 different images, one of just the reds, one of just the greens, one of just the blues. When you put those back together and assign blue to the blue image, green to the green, red to the red, you get a full natural color image. That's incidentally, that's the same way Technicolor movies work. It's actually photographed through a red, green, and blue filter and onto monochrome or black and white film stock, and then it's projected through red, green, and blue filters to recreate the color. Narrowband astrophotography gets very interesting. I mentioned earlier that gases become excited or ionized when they're energized. That means they're emitting light. They're actually glowing like a neon or a fluorescent lamp. And every element will emit light at specific colors or wavelengths. Wavelength and color kind of mean the same thing. But you can identify the element by the color of the light because every element is unique. It has a unique combination of light that it will emit. You can also isolate specific elements by using a filter that will only capture that color of that element. So when we photograph sulfur, hydrogen, and oxygen, that SHO combination of filters, sulfur is a very deep red color. That's the color it emits, or one of the colors it emits. Hydrogen emits also a very deep red, but not quite as deep a red. It's just a little bit less red, but they're so close together that visually you probably wouldn't tell them apart. Oxygen is another very common gas, and it emits light in kind of a blue-green or cyan color. So you have these three different elements. You can use three different colored filters and capture an image of just the sulfur, just the hydrogen, and just the oxygen. And then assemble, like we did a red, green, blue image, we can assemble an SHO image using sulfur, hydrogen, and oxygen. So here's an example. This is the Elephant Trunk Nebula. And if you look at the image of oxygen, the image of hydrogen, and the sulfur, you'll see there are differences. They don't look the same. The oxygen is much brighter near the top. Hydrogen is brighter in the middle. Sulfur is brighter near the bottom. So if we assign these the actual color of the gas, so the red for sulfur and hydrogen and cyan for oxygen, and then add the stars back in, we can get a kind of natural color image. The problem with this image, or the drawback of this approach, is you can't really tell from the image the difference between sulfur and hydrogen because they're so close to the same color you can't tell them apart. So while it's an interesting picture, it's less useful in terms of knowing what you're looking at. So instead of using sulfur, hydrogen, and oxygen exactly as they are, we translate the colors. So we translate hydrogen from being red to green. So it's still less red than sulfur, but we just make it a lot less red than sulfur and move it towards the green. And then so that we don't run into oxygen, we actually move the oxygen color from cyan or blue-green over to blue. So we have sulfur, hydrogen, and oxygen mapped as red, green, and blue, three separate colors. Now, if you look at the image on the right, this is the same sulfur, hydrogen, and oxygen, but mapped as red, green, and blue. And now you get a much more useful image in terms of knowing what you're looking at. So here it is just closer, assigning red, green, and blue. This is often called an SHO image or the Hubble palette. This idea was kind of pioneered in the 1990s with some of the early Hubble images, in particular the Pillars of Creation. And one of the reasons it's so popular is because it maintains the chromatic order of the colors. So the most red color is red, and the lesser red color, which is hydrogen, is green, and the least red color, which is oxygen, is blue. So the colors are in the right sequence. They're just translated to make the image more informative and more useful to us, much like you might translate a text or a poem or a song from a language you don't speak to a language you do speak so that it would be of interest to you. So this is the California Nebula. Hydrogen really dominates most of the nebula. Hydrogen is the most common element in the universe. So if you just look at it normally, it would be dominated by the red. But when you use sulfur, hydrogen, and oxygen and separate the colors, you find a lot more detail and a lot more interesting things going on. The visible light that we're using is just a very small part of the total electromagnetic spectrum, and that ranges from radio waves and television to microwaves, infrared. Visible light is just really a very tiny piece. And then ultraviolet X-rays and gamma rays. The only electromagnetic radiation or form of light that we can see with our eyes is visible light, and that's what we call red, green, and blue. So the Hubble telescope, for instance, views mostly in visible light. That's how the camera and filters are designed. So it's working primarily in visible light. The James Webb, one of the newer telescopes, is tuned specifically to photograph with infrared light. So it's photographing things in this part of the electromagnetic spectrum, and there's some real advantages to that for some things. But there's an example of a photo from the James Webb, and remember, this was all captured using infrared wavelengths that were then translated to colors that we can see. Here's a comparison of the Hubble and the James Webb. And one of the things you'll notice with infrared is you see more stars. And that's because infrared is able to look through a lot of the dust and see what's going on beyond it. This is a deep field. Probably the main motivation for using infrared on the James Webb is that our universe is expanding. And as it's expanding, the distant objects become redshift. In other words, they become more red, and they get more and more red till eventually they go from visible red into the infrared where we can no longer see them. So they're invisible to telescopes like the Hubble because the light is now in the infrared spectrum. Since the James Webb is working in infrared, it can see more of these distant galaxies that are billions of light years away and billions of light years old, and see things in the distant universe that Hubble can't see. But there are also other kinds of telescopes in other parts of the wavelength. There are radio telescopes that are capturing data in the radio wavelengths, and there are X-ray telescopes like the Chandra that's capturing images using X-rays instead of visible light. And there's even a microwave known as the cosmic microwave background. And you can think of this as the earliest light that was given off by the Big Bang 13.5 billion years ago. And it has cooled from being a very, very, very hot ball into a very large, diffuse, much cooler. So now it's emitting light instead of invisible light or even infrared or radio waves. It's in the microwave wavelength. So we have telescopes working all across the spectrum from microwaves, radio waves, infrared, visible, and even X-rays with the Chandra telescope. And you will sometimes even see images that combine visible and infrared or visible and X-ray to create more informative images so you can see combinations of things that are happening. So, kind of in summary, astrophotography can be used for pretty pictures of space, study the composition of our universe. Cameras on telescopes are the things that collect the light that scientists use, and that is how we learn about our universe, is by studying its light. So if you have any questions, drop those in the comments down below. I hope you found this useful and informative, and I hope it answered some of your questions about what astrophotography is and where the colors come from and how it's used. So with that, I hope you have a great day today and an even better night tonight under a clear, dark sky. Thanks.